inside and outside a sphere. No, it's a solid sphere with radius r and total charge q. So I'm starting with the outside, where small r is bigger than radius big R. What's our Gaussian surface in this case? I'm using orange. No, I'm feeling green instead. This is our Gaussian surface. In this case, So according to Gauss's law, the flux through a Gaussian surface equals to 1 over sigma naught degree of liberty times the total charge enclosed. So in this case, the total charge enclosed is all these, which is Q. So the right side of Gauss's law is just this. The left side is it's the infinitesimal area of our Gaussian surface, dA. So, it's a sphere, and we're using spherical coordinates. This gives us 4 pi r squared E equals to Q over sigma naught. And E points radially outward, so we're simply adding a unit vector r over here. So this is our electric field for this case. We're calling it case 1. Now our task to do here is finding out the potential V. Do it in blue. No, it's probably navy. Sorry about that. So the potential is minus the integral of our electric field times dl from infinity, which is our required reference point, to r, point r. We're plugging in our electric field and dl. 1 over 4 pi sigma naught q over r squared. Oh, what's wrong with the pen? Damn. R squared. Oh, it's probably the problem of the screen. I don't know. Oh, it's okay now. Unit vector r times dr unit vector r, and this gives us minus, we're taking out a constant, q over 4 pi sigma naught, the integral of 1 what's happening? Is it because I'm charging? No. dr, and this gives us minus 1. Come on. Hello? Okay, I'm very annoyed right now. Just gonna do it faster. It gives us minus 1 over r from infinity to r. Canceling these two minus signs gives us q over 4 pi sigma naught 1 over r. Yes, this is it. And as required in the problem, we're computing also the gradient of V. So the gradient of V, I'm doing it here. Gradient of V equals to partial derivative of R of Q over 4 pi sigma naught 1 over R in the R direction, which is minus Q over 4 pi sigma naught 1 over R squared in R direction. According to this relation, we know that our result for the potential in this case is correct, because this corresponds to this via this relation. So we're done with the outside case. We're doing the following case inside. So this is our solid sphere with radius r, and our Gaussian surface in this case is inside this solid sphere. So the charge enclosed, inside, where small r is smaller than big R, as it should be. I'll call it case 2. So we're doing Gauss's law again. 4 pi r squared E equals to 1 over sigma naught. What's the charge enclosed? It's the total Q, but times the fraction between the two volumes of our spheres. So Q times the volume of a sphere is 4 over 3 pi r to the third. Same for our big R. And here things cancel out pretty fast, right? And also here. So our electric field in this case is 1 over 4 pi sigma naught times Q over R squared in the R direction. Am I missing anything? No. Okay, this is the R. Now the trickier point comes to when we do the potential, because we know that even in an area where the electric field is 0, the potential doesn't have to be 0, and it probably won't be 0. So we'll have to separate the regions where the field, electric field, is different. So VR is first from infinity to big R, and its electric field is what we've done in the first case. What is it? Q over 4 pi sigma naught times 1 over R squared in R direction, dr in R direction, minus sign, very important, I always forget, minus, which is actually plus minus the potential inside the sphere, because potential also follows the superposition law. So from R to R, little r, we have our field 1 over 4 pi sigma naught Q over R to the third in R direction times dr in R direction. Okay, the pen's messing with me. Again, it's fine. we're taking out a constant. This is very tiring, like explaining everything while writing. So minus 1 over r from infinity to r, canceling these, minus 4 pi sigma naught q over r to the third dr from big R to small r. This thing right here we have q over 4 pi sigma naught times 1 over r minus 1 over 4 pi sigma naught times q over r to the third times r minus big R. I feel like we're missing something here. Yes, forgot r. Damn, I'm stupid. So this here, r dr, and it's just small r squared minus big R squared. Okay, I'm sorry about that. Oh, and 1 over 1/2. We're done. We're done here, right? Are we done? Yeah, we are. Now let's compute the gradient of potential in this case. The thing goes to 0. Minus 1 over 4 pi sigma naught q over r to the third, a half, I'll put it here, and this here, we have 2r, and these two cancel, gives us minus 1 over 4 pi sigma naught q over r to the third times r. Right, and this corresponds perfectly to our electric field in this case. So we're done for problem 2.21. Goodbye.